This video is on equilibrium of weak acids. I'm going to do two types of problems, but they're both going to be very similar, and we're going to be using an ice table. So the first one is where we're given a pH, and then we're asked to calculate Ka. So here's the pH, and then they gave us something else, some other information. So let's go ahead and set up a ice table, because as we know, weak acids are not going to dissociate fully. So we're going to have this as our equilibrium. So HBrO, and that makes H plus BrO minus. And we're going to set this up. And we're going to think of these as these boxes again, just like in the last chapter. And we're going to sort out what they're giving us and figure out what we need to solve for. So first of all, in keeping with the theme this year, we're going to write a description for what we're trying to solve for, which is Ka. So Ka is going to be the concentration of H plus at equilibrium. So we have to be really accurate about how we describe what we're solving for. Okay, and this is the concentration of the hypobromite ion at equilibrium, and divided by HBrO at equilibrium. So these need to be the amounts from the E line. That's why I wrote the little EQ. So these are those numbers that you have to plug in right here. Okay, so let's sort out what they're giving us here. So this is something. So it says pH of a 0.063 solution. This is the initial amount, okay, of HBrO3, the initial concentration. So that would be this number here, 0.063 molar. These are going to be zeros because you won't start with anything. Now, an interesting thing here on this question is what is the pH? Which box are they giving us? So if you remember, pH is the negative log of the hydronium concentration. This is actually the hydronium at equilibrium. Like when all this has gone to the right as much as it will, as we know it's weak, so it won't very much, but it does. When all that is said and done, then you calculate the pH. This is actually this number that they're giving us. Remember, the ice table is concentrations, okay, or pressures, but when we're working with aqueous equilibrium, like the next month or so of class, these need to be concentrations or the molarity. Okay, so that's what this number is actually the pH. So, and to get the hydronium at equilibrium, it's going to be 10 to the negative pH. So this would be 10 to the negative 4.95. We have 2 decimal places. So the result here should have 2 sig figs. So if we go ahead and enter that in our calculator, we get 1.1 times 10 to the negative 5th molar. Okay, now this amount is actually, so that's this amount, and as we know, this goes up by x, and this goes also up by x. So whatever we got here is actually the amount of the hypobromite ion as well. So this is going to go up by x. This goes up by x. So these two are going to equal each other at equilibrium. So this actually equals the hydronium, and it also equals the amount of BrO minus at equilibrium. Okay, so as you see, we have 2 of the numbers we need. So that and that are going to go here and here. So now all we need is this, so we can get this number here. Okay, so this is going to go down by x, and now that we know that x, this also equals our x here. So this amount at equilibrium is going to be 0.063 minus x. Okay, so now that we know what that is, we can plug this in also. So we're gonna put all of these numbers here in our equilibrium expression. So this is going to be 1.1 times 10 to the negative 5th squared over 0.063 minus 1.1 times 10 to the negative 5th. Okay, and we enter this in our calculator, and you should have 2 sig figs from this number. So I get you get like 1.99 something something times 10 to the negative 9th times 10 to the negative 9th. Okay, unitless as KAs and KBs are. So that's that problem. So let's go ahead and go on to the next problem. This is slightly different, but you'll see that the strategy is going to be the same, is that we set up our ICE table and then we organize the information by figuring out what they're telling us and not telling us in these boxes here. Okay, so let's move on to another example. So it says, this one says, calculate the concentration of all species present and the pH of a 0.020 molar hydrofluoric acid solution. So they're giving us some different information here compared to the last question. So notice the last one, they gave us the hydronium concentration. So on this one, it says calculate the concentration of all species present. Okay, so that means what they're really asking us here is calculate this number, and then we'll take the negative log to get the pH and calculate this number. So that's what they're asking us to solve here. And they gave us, this is the initial. So that is HA initial. A is generic for acid, just any acid. Okay, so this is 0.020. These are zeros. This is going to go down by X. This will go up by X. And this will go up by X. So something interesting is happening on this one. You most likely will not be able to use the assumption rule, and I'll show you why. That's actually what the remainder part of this video is going to go into. So notice that this is actually, as far as weak acids, this is actually kind of strong, sort of, relative to other weak acids. This is actually getting up there, hydrofluoric acid. So that means more than other weak acids goes over here and makes ions. So that's going to make X kind of big. The other thing to consider is this right here. This is actually pretty small. This is much less than 1. So when you have this combination where this is low, the initial, and the Ka is sort of big, then we're most likely not going to be able to use the assumption rule, okay, to get these numbers. So this is going to be 0.020 minus X. This will be X, and this will be X. So I'm going to do this in a different color pen here to show the assumption. So this is using the assumption rule, and I'll show you what happens. So we're assuming that X is too small, that it will not affect that number. But like I was saying, the Ka might be big enough to where it might actually affect that number. So using the assumption rule, we're going to have 7.2 times 10 to the negative fourth equals X squared over 0.020 minus X. So we're gonna assume this is nothing, and we'll solve for X here, and we end up getting, using the assumption rule, we end up getting X is equal to the square root of the Ka, 7.2 times 10 to the negative fourth times 0.020. So we actually get 3.8 times 10 to the negative third. So we're going to do a this is called the 5% check on this problem. So it's said to work, the assumption rule is said to work when X is less than or equal to 5% of the initial amount, the initial acid amount concentration. So what we're going to do is we're going to put what we got using the assumption rule. So we're going to go X over this. And it needs to be less than or equal to 5% for the assumption rule to work. So if we plug in what we got for X, so we'll put 3.8 times 10 to the negative third over the initial amount, which is 0.020. Okay, change it to a percentage, and we actually get 18.97%. Okay, so this is greater than 5, so the assumption rule will not work. The assumption rule won't work here. Okay, so that means we're going to have to use the quadratic formula or use a graphing method to solve this problem. So I'll do that on the next slide here. Okay, so I'll write out my equilibrium again. Okay, and this was 0.020 minus x. This is x. This is x. Okay, and so we're going to get 7.2 times 10 to the negative fourth equals x squared over 0.020 minus x. Okay, so if we set this up, we're going to get 1.44 times 10 to the negative fifth minus 7.2. I ended up using the quadratic, it looks like, in my notes. Okay, and x is going to be equal to 3.45 times 10 to the negative third. Okay, and the amount of H plus is x. This is also equal to the amount of F minus. So it says calculate all the species. So this. All the species OH also exists in the solution. So we need this number also. Okay, so this is going to be equal to x 3.45 times 10 to the negative third molar. Then our amount of HF is equal to 0.020 minus x. So this is going to be 0.017. So we see x was actually a significant amount of the initial amount. So it actually, put a solid dent in that number. That's why we couldn't use the assumption rule. Because we're assuming x would not affect this number, and we see that it actually did quite a bit, actually. So OH also is in the beaker, so that's another species that's present that we need to solve for. So OH is going to be KW over the amount of H. So for this I get 2.6, and we should expect this to be tiny because it's an acidic solution. And lastly, we can get the pH, which is the negative log of this number. So I get, for the pH, 2.46. Okay, so on the so here's the your turn problems. You'll see that number 1 is really similar to the first example. I kind of went in order here. There's a little bit of a curveball here, and then on number 2, it should be very similar to also the one that I did. Okay, so let's see what you guys come up with at the end of our video.